Okay, so the next light that we are interested is an area light. Now this area light is a little bit different from the object light because this is an invisible area light. Okay, so let's use something that writes. So invisible light. Okay, so what do I mean by invisible light? Like it is an area, but our rays do not actually intersect with this. Okay, so in other words, it is not a real object, in the scene. Okay, but it is defined by an area. So there are different ways of defining an area light. You could use the edge vectors and things like that. But let's say, for our purposes, if we define something like this, okay? So let's say we have a center point, okay? Let's call this Q, the light center, and we can define the size, okay? Let's make our light square, okay? Size, basically, it's going to be the size. So that is the position, the 3D position of the light in the world, okay? And the size determines the extent of the light. But we must define the orientation of the light also, okay? So the orientation of the light is defined by a vector, okay? So now this light is like looking like this, okay? So the normal vector of light. Okay, so it's like that. It's going to be defined by a position, size. Because we have a single size, it is going to be a square. Okay. If you want to have like rectangular area lights, then you may define edge vectors. Okay, or different sizes for different axes. For now, we are just going to use the square lights. And we will have a normal vector of light. So the normal vector is a vector that is perpendicular to the plane of this light. Okay. Now, it is important to remember that these are invisible. So rays do not intersect with this light. Just like a point light. Just like our rays cannot intersect a point light, our rays will not intersect this light. Okay. But we will use it for illumination computations. So this light is also going to be defined by its radiance. Okay. Will be defined by its radiance. So how is it going to work? Let's say we have a point here, okay, point P on a surface. Now we are going to compute the contribution of the light to this point. We are going to randomly sample a point on the light source, okay. So let's say we randomly selected this point, and then we will it will be defined by its radiance. So for simplicity, our area lights will have constant radiance. Okay, will be defined by its radiance. So this will be constant across the surface of the light. Surface of the light. Okay, so it's a uniform light source. What we are going to do is, when we want to compute the shading at point P, we are going to connect it to our light source by randomly selecting a point. Okay, so this is important. And then let's say this becomes the incoming direction. This is our surface normal. Okay, surface normal. And this is going to be our direction theta.